Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away
46, 56 degrees.
Thank you. I really appreciate the Robinson for inviting me to come here and talk about one of my favorite things. Being a professional biologist and amateur astronomer, I really get the best of both worlds. And so this is something that I have lots of fun with. What I want to try to do tonight is to communicate a little bit of science to you, as well as speculate about what might be happening out there. And of course, as you see here on the slide, there's all kinds of questions that we can ask, and we're at a rather unique time when we're starting to leave the planet. Although we're taking the first baby steps, but obviously as a biologist, I'm interested in the possibility of life elsewhere in the solar system, and obviously if life might exist in other solar systems somewhere out there in the galaxy. What I want to do is to start initially saying a few words about how we go about looking for life in our own solar system. The question is life on Earth, just an n equals 1, or are there environments elsewhere in the solar system where living organisms conceivably could be? And of course, one of the things that NASA has been doing is going to Mars repeatedly with a variety of different rovers, including the one you see here, which is called Curiosity. And I think Curiosity is sending us a message here. When we first put orbiters around Mars, one of the really fascinating things that we saw are images like the one you see here. It clearly looks like dry riverbeds. And you can see features like this all around the planet. And so clearly there had to be some fluid flowing on the planet in very ancient times. And really the only thing that could carve out the kinds of geology that we see here is liquid water. Mars today is cold, dry, but clearly there's evidence that in the early history of the solar system, the early history of Mars, it was warmer and wetter. And that is very interesting, not only to space people, but also to biologists. One of the reasons why we know water existed on the surface of Mars is not just those dry riverbeds, but what they call these blueberries. These things are about the size of a BB. They're composed of hematite, and this is a mineral that forms in water. And that's very, very instructive. So clearly, Curiosity, as well as the previous rovers, has shown that there's a lot of geology up there, a lot of mineralogy that shows that water existed on the surface of Mars at one time in the past. There's actually a lot of water on Mars, but it's frozen. It's beneath the dusty surface in the form of permafrost. Now, as a biologist, I like to speculate that if you drill down far enough where it gets warmer, you'll have a lot of liquid water. The atmosphere is mostly CO2. There's probably a lot of other gases up there. And so there would be an opportunity for bacteria to be living and metabolizing and growing below the surface of Mars. Just like it turns out that bacteria can live thousands of feet below the surface of the Earth. And so if they can do it here, they can do it there if life, microbial life, arose on Mars in its early history when it was wetter and warmer. Mars is not the only place that we're excited to look at. This was a report on a NASA press conference that occurred just a few days ago, where there's a lot of new data coming out about the moons of Jupiter as well as Saturn. And of course, what we discover, particularly one of the larger moons of Jupiter called Europa, one of the 4 big moons called the Galilean moons, because Galileo is the one who discovered them with his telescope. These moons have a very icy surface, but there's a lot of evidence that has accumulated over the years from spacecraft that we've had in orbit around Jupiter, called Galileo, amazingly enough. There's a liquid water ocean below that icy surface. And what we have recently discovered, of course, is that some of that liquid water comes through those cracks. It looks like a cue ball. It's very smooth from a distance. Those cracks are due to the fact that as Europa orbits Jupiter, it gets squeezed back and forth. And that produces what we call tidal heating. If you took a squash ball and held it in your hand and just squeezed it back and forth, it gets hot. You can prove that to yourself. Same thing happening here. The gravity of Jupiter squeezes Europa, meaning that there's an internal heat source, meaning that below the icy surface, there's liquid water. Now, what we have discovered recently, and you can see happening right here, is that there are icy geysers that are coming out of some of those fissures. And that is extremely exciting because that confirms the fact that there's liquid water below the surface. But it also turns out that there can be organic molecules in those geysers. This is a satellite of Saturn called Enceladus. And you can see these geysers coming out here. These are images taken by the Cassini spacecraft that's been orbiting Saturn for over 10 years now. Cassini has actually flown through those geysers and is able to detect the molecules that are present there. And they can find hydrogen, methane, a lot of other molecules that you see listed here in the slide. Now what's exciting about this is that, again, on Enceladus, there's liquid water below the surface, but there's also organic material in those geysers. Now, here's the thing. Carbon monoxide, methane, hydrogen, these are all molecules that bacteria can use for energy and as a food source. Because there are bacteria on Earth that do exactly that. In addition to that, there are some other simpler organic materials and some more complex organic materials. So, water, organic materials, that is really what you need for life as we understand it. Now, I'm going to argue for biological chauvinism. Now, some people might disagree with this, but this is the argument I'm going to make. Life is water-based and carbon-based. That's what we are, okay? And all the other organisms on this planet. The reason why I say life is water-based is because water is the best solvent of anything that we know of, okay? Its solvent characteristics, its chemical behavior exceeds that of anything else. You know, some people have speculated maybe ammonia-based life forms someplace, but ammonia can't even touch water for its chemical diversification. Carbon-based. Well, carbon is actually common in the universe, okay? And you can find carbon compounds, organic compounds, in meteorites, in nebula, in gas clouds. And so clearly, organic molecules can be produced under non-biotic conditions, okay? And carbon is a much more diverse and versatile molecule than others. Again, some people speculate, well, what about silicon-based life forms, okay? But silicon, again, doesn't touch carbon in terms of its ability to form long chains and participate in a wide variety of diverse chemical reactions. So that's the argument I'm going to make. If we find life somewhere else in this solar system or somewhere else, I'm going to bet you money that it's water-based and carbon-based. And you can argue with me about that if you want to. Okay. So that then brings us to the question of where are the aliens? Okay. Well, people started looking for aliens back in the 1930s. The guy that I'm going to highlight right here is Frank Drake. He's a radio astronomer. He and his cohorts built this radio telescope in the late 1930s. And after that, one of the things they did was to try to use it to listen for intelligent radio signals from outside our solar system. So Project Ozma is what it was called. It was the first SETI's, Search for Extraterrestrial Intelligence. They listened to 3 nearby stars and unfortunately didn't hear anything. But that's a pretty small sample. Years later, at a meeting dealing with SETI and other related things, Frank Drake came up with the equation that you see here, where basically what we're doing is calculating the probability of intelligent, technological alien civilizations out there. So N, sub-galaxy, is the number of stars in our galaxy, and that's like 400 billion stars. The fraction, population 1, these are stars that are sun-like, okay? F, solar mass stars similar to our sun. Here's the problem. Stars that are too big burn out too fast. So you want a star that's just the right size, that has a long lifetime, where, you know, given the right conditions, life could, you know, develop on a planet the right distance from that particular star. Then the question is, are there extrasolar planets? And until recently, we didn't know that they even existed, okay? And then can we find planets that have the possibility of habitable environments, okay? And then, of course, it's a matter of, on those planets, does life actually start? So first, let's talk about planets. You got to have a planet, as we generally understand it, or a moon, possibly, with the right conditions. And so how do we go about searching for planets? Well, I'm going to just tell you one way we do this. We can look at the light curve of a star, and if there's a planet that passes in front of the star within our line of sight, you notice that the light curve dips right here. We have identified thousands of stars that have planets using this method. There are other methods, but I'm just going to mention this one. Now, if we just consider our own sun, this is Venus passing in front of our own sun. So we would be observing these kinds of events. We call it a transit around other stars. And so we have found thousands of extrasolar planets. The evidence is such that there's probably more planets in our galaxy than there are stars. So we're talking about potentially hundreds of billions of planets out there. The problem is how many of those are going to be the right distance from the star so that liquid water can exist. Not too far, not too close, what they call the Goldilocks zone. This slide is a couple of years old, and I use it just to illustrate the fact that a lot of these planets are real big like Jupiter, but we're finding over 1,000 planets that are Earth-sized. And some of these planets are actually at the right distance. So Kepler 452 is a star where there's an Earth-like planet in its habitable zone, its Goldilocks zone. Kepler 186 is another one. There are literally dozens and dozens of stars that have planets in which they're in the Goldilocks zone of those solar systems. This is another slide here where we look at several different stars. Our sun is a G-type star. The K stars and M stars can also be potential places to look for Earth-like planets. And we have found them there. You can see in each of these cases here, planets that have been found around those types of stars. And these planets are in the Goldilocks zone. Okay? So what this tells us in the Drake equation is that there's lots of planets out there. Now, these planets can vary in size. Some are Earth-sized, some are what we call super-Earths. because they're 2, 3, 4 times bigger than we are, okay? But here's the thing, they're rocky planets like Earth, as opposed to a big gas bag like Jupiter or Saturn, okay? So now we can say here that we kind of know what that number is. It's going to be pretty big. Now, what's going to happen in the next few years is that with new telescopes coming online, we're going to be able to look at the atmospheres of some of these planets in the habitable zone of some of these stars, and we're going to be able to look for certain kinds of gases, oxygen, methane, other things, you know, water vapor, other things that might contribute to a suitable environment for life, okay? We're not going to get there physically anytime soon because, you know, traveling over interstellar distances is still way beyond our capability. But at least by looking at light coming through those atmospheres, analyzing it with a prism, which creates the rainbow, we can actually identify different kinds of molecules there. And so that's the beginning. Okay, now what else can we do to search for life in space? Intelligent life, particularly. Well, we can listen for it. We can listen for radio signals that might originate from some intelligent civilization out there. That's what SETI was all about, search for extraterrestrial intelligence. There's been a lot of SETI projects over the years, okay? They usually involve these large radio telescopes like the one here in Australia, or the radio telescope at Arecibo in Puerto Rico, okay? More recently, SETI is making use of a bunch of smaller radio dishes. The idea was called Baby Cyclops, but this is funded by Paul Allen, who made his fortune with Microsoft. And eventually there will be hundreds of these little dishes being able to listen for signals that might originate from a extraterrestrial society. These dishes can be linked together so they act as a much bigger dish in terms of gathering their radio signal. So we've been doing SETI for a long time, and we haven't really heard anything that we can identify as being extraterrestrial. But that doesn't mean that we should stop, okay? The one sure way to guarantee a lack of success is not to do it. Well, back in the early 1950s, Enrico Fermi, who was one of the great physicists of the 20th century, helped to build the first atomic reactor during World War II for the U.S., was sitting down at lunch one day with a bunch of his buddies, and they were just kind of, you know, thinking about things in general. And he posed a question to his friends: where is everybody? I mean, if extraterrestrial societies exist out there, why haven't they gotten here? Why haven't we, you know, made contact with them? Well, there's a lot of reasons, and we'll talk about a few of those. But one of the possibilities is that our radio signals are going out there. And so eventually maybe somebody's going to hear us and respond to that. There was a book called Where is Everybody? And some of the answers to Fermi's paradox is we're the first technological society. Maybe they haven't had time to reach us. Maybe they stay at home and surf the web. We haven't listened long enough. They're somewhere, but the universe is stranger than we think. The supernova got them. You know, any number of possibilities there. Of course, the Star Trek version is they're unable to respond or maybe unwilling to respond, a quote from Spock. So it's possible that the Star Trek Prime Directive actually functions out there. And we're just a pre-warp society that nobody is really interested in at this point. Have they been here? Well, there's all kinds of UFO enthusiasts out there, but I doubt that very much. Calvin and Hobbes say, sometimes I think the surest sign of intelligent life in the universe is that it hasn't tried to contact us. Carl Sagan would say extraordinary claims require extraordinary evidence. So I don't think they've been here yet, but we just don't really know. But just listen. I guess they found us. All right, that's my presentation. So let's do some Q&A.
All right, I have a microphone and I'll come to you. Who wants to start with the first question? All right. Do you want to yell or do you want the mic?
I'll just yell,
Okay.
because I'm well. Define life. Because that's basically what you're looking for, is if there's life in another planet or elsewhere. But our definition may be limited.
That's true.
And it
Life,
also may be limited in the venue that we're taking to try to contact those individuals or beings or whatever.
definition of life is not easy.
Because you
it's-
based it on water and carbon. This whole thing is based on water and
Well,
carbon.
that's because we're most familiar
Because
with
that's
that.
how we survive.
Right.
But-
I mean, there
but
could
we're
always be
talking about
other
something outer
possibilities.
space, thousands and thousands of years away from us.
Oh, sure.
How can we assume that they're based on the same chemistry?
Well, you can't make that assumption 100%. Okay, what I'm arguing is what's most probable, not what necessarily
Most
could happen.
probable for us,
Well, most probable based on chemistry and physics.
our chemistry.
Well, chemistry and physics is the same everywhere. It doesn't vary.
Is it?
No, chemistry and physics is the same throughout the entire universe. And the chemist or physicist could prove that to you. But life is hard to define. It's like the Supreme Court said about pornography. They can't define it, but they know it when they see it. Who else?
I have one while everyone's thinking. So my question is, what do we do when we find life? What's the next step?
Well, it depends on what kind of life it is. I mean, I think that if we find life elsewhere in the solar system, it's going to be microbial. It's going to be bacterial life. Okay. But life somewhere out there in space could be anywhere from bacteria to higher animals. And of course, you know, the life on Earth is very diverse. So if we find living organisms, higher organisms somewhere else, they're not going to be anything like anything we've seen on this planet. Okay. But you know, even intelligent creatures somewhere else could be very, very bizarre. Even though the chemistry might be the same, they could be extremely different in so many ways. So, who knows? Yeah.
I'm sorry, it's just that it's quite, unless you are an alien, I don't think that you can possibly claim that you're not bound by human dynamics, human quadratics, human ways of understanding the world or formulating the world. And so physics, yes, strives to be objective. And
No, there.
so does mathematics, and I would love for that to be perfectly objective, but at the moment I think that we are kind of bound by the human fact of existence. If you have a brain, I think,
Well,
right, we have brains. And
I mean, extraterrestrial intelligence could be bizarre compared to the way we think. I mean, their way of thinking, their culture
I
could
would
be
tend to-
almost unintelligible to us.
Right,
You know?
and I would love to believe in ultimate facts and objective facts, but you also have a brain, and so you're bound by what the brain thinks is fact. So it's quite possible that, yes, there is a stranger reality out there that we couldn't possibly conceive of, but I would like to believe that humans can do so. But ultimately, I mean, I don't really want to put my money on believing that intelligent life is bound by the probability that it's going to be based on carbon and water, biological and chemical molecules, and nor do I want to really truly believe that we are capable
Well,
of
I mean,
asserting that
people.
we're
I mean, some
capable of
science fiction authors have speculated that life could be based on some other kind of
that, like
basis.
electromagnetic-
I mean, Fred Hoyle, who was an astronomer years ago, wrote a novel about this huge, giant gas cloud with electrical currents flowing in it and
That's
what have you.
something
That was an intelligent life form. Okay, so that's something totally different than the kind of biology, you know, that would be familiar to us.
I mean, the whole electromagnetic spectrum. So why should we even have to believe that intelligent life is based upon even genetics? Like, intelligent life could be light or sound, and I don't think I have yet grasped that intelligent life could be beyond matter, even.
A non-corporeal type of life. Well, I mean, that again is speculated about in sci-fi, but we just don't have any. We currently don't have any rational basis for that.
Not yet.
Well, okay.
But I mean, you have to start someplace with certain, you know, conceptions and work your way there and see what you discover.
That's all we can do at this point. But we can also open our minds to other possibilities as well.
Oh, sure. Yeah.
Okay, I think it's very interesting that you said earlier that whatever life forms we perhaps may find years from now, tomorrow, or 10 years, or 75 years from now, or 500 years, that they're basically, and I'm not quoting you, okay? I'm just, you know, my mind's free. That they're basically bacteria. And I think that that's so arrogant in our perspective on things. And I'm not a scientist, I'm an artist. So, you know, I'm a little open-minded to things, and that was just something that crossed my mind, that if you think that, oh, we're just going to find some other life and it's going to be a simple bacteria, I think that that's pretty arrogant.
Well, it depends on the environment that you look at. If we find life on Mars,
water and carbon.
if we find life on Mars, it's going to be microbial, because clearly there's no civilization, there are no higher organisms walking around on that planet.
That we know of for our
Well, we know there
knowledge,
isn't
that
anything
our
on the surface
technology
anyway.
tells us.
You know, well, I mean, anything is possible, okay? But what I would argue is that as we go along, you have to consider probabilities. You know, what is most probable?
Well,
And that's
the difference between you being a scientist and me being an artist.
Well,
Because the
that's
probability
true.
in my mind
But I mean,
would be-
it's simply a point of departure. You know, I don't have the final answer. Nobody does.
Nobody does, yeah.
You know.
All right, we got a
So
question down here.
She and I were sent by Pluto to attend this meeting, sorry
Okay,
guys.
Hi, Dr. Cran.
Yeah.
Mark Chapman. Carl Sagan, in his book Contact, has talked about the different timelines that aliens might communicate with us. And he expressed some concern in his book that maybe they're going to try to communicate, if they do communicate with us, or they communicate and we try to detect it, it might be on a time scale that's far off from the time scale that we are listening for. Have you thought about that concern, and what do you think the odds are that we're just missing it because it's too quick or too slow that we just can't detect it?
Well, that's certainly possible. I mean that is true. Okay. You know, what time for us could be extremely different than time for an extraterrestrial intelligence or society somewhere else. Very true. You know, time for us is based on the rotation of the Earth. Okay, time for somebody else could be based on something, you know, entirely different. And so that's a fact. You know.
Okay, I think we have time for one more. And it can be me and everybody else.
Oh, yeah.
Okay, so we know that there are many scientists out there that are working on this, that are searching for life in outer space. Maybe the most famous, to at least, you know, popular culture, being Stephen Hawking. So based on their work so far, their findings so far, if you had to take a guess as to how many years or decades or centuries from now, when you think we will discover alien life, what would your speculation be?
Okay, two-part answer. Discovery of life in the solar system, on Mars or one of the moons of Jupiter or Saturn. I think that will happen within the next century. Just depends on how fast we go out there. Okay. When might we make contact with an extraterrestrial intelligence? There's no way to know. And again, how many intelligent societies exist in the galaxy at any one time. You know, there could have been other intelligent societies that have come and already gone. There may be some that come when we're gone, you know? And so we have no data as to how many there might be and what the time scale of their existence is over the lifetime of the galaxy. So that's really a question that cannot be answered. Unfortunately.
So we just have to wait and see.
We just have
right?
to wait and see. That's
Well,
right.
please join me in thanking Dr. Lucas for being here tonight.